Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today we discuss a few questions from the tutorial. So for this session we'll discuss question number 1 related to the radioactive decay. So this is a question. If we have 3 radioactive sources, each have activities of 1 microcurie at T equals 0. So we have 3 half-life here, 1 second, 1 hour and 1 day. So I will try to answer question A and C, and I will answer question for 1 second and 1 day half-life. So you can try for 1 hour by your own. So here question number 1A, how many radioactive nuclei are present at T equal 0 in each source? So source we have here 1 second and 1 hour and also 1 day, but I'm trying to answer these two. Right? So first of all, remember the equation for try to find a number of radioactive decay, which is the equation will be N equal A over lambda, which is A is the activity. So the activity that we have here is 1 microcurie, and for lambda we call it as a decay constant. This is a decay constant. So the formula for decay constant is lambda equal to ln 2 over T half-life, and ln 2 is equal to 0.693 over T half-life. So we should start with n equal to lambda. Find lambda first for 1 second. Okay, so lambda for 1 second is equal to 0.693 over 1 second. So we have here 0.693 for decay constants, decay per second. And then try to find n for 1 second. For half-life 1 second, so we have A, so we need to find the value for A, which is A is a 1 microcurie, but 1 microcurie, okay, this is, I need to find one box here. Okay, so 1 microcurie is equal to 1 times 10 power of minus 6 times 3.7 times 10 power of 10. You can get the value in the decay per second, which is 3.7 times 10 power of 4. Okay, sorry, this is it should be per second. Okay, this must make a mistake here. This is second. Right, so now we have 1 microcurie is equal to 3.7 times 10 power of 4. So this is will be A. So the A will be 3. We are using this equation, n equal to A over lambda. So A is 3.7 times 10 power of 4 decay per second. This one is decay per second. Okay, decay per second. So lambda is 0.693 per second. So the answer here is 5.34 times 10 power of 4. So this will be answer for source 1 second half-life. So the number of radioactive nuclei. So this is the number of the radioactive nuclei. So we try to do for 1 day. Alright, for 1 day. It's quite similar. So for 1D, find lambda first. For 1D, so it is equal to 0.693 ln 2 over half-life. Okay, the half-life is actually 1D. So 1D is equal to 24 hours. 1 hour is equal to 60 minutes. 1 minute is equal to 60 seconds. So we convert to the second. So the answer here is 8.02 times 10 power of negative 6 per second. So number of radioactive nuclei is equal to, so number of radioactive nuclei is equal to A over lambda. So remember the same equation here, A equal lambda. A similar here because 1 microcurie is 3.7 times 10 power of 4, and lambda is here 8.02 times 10 power of minus 6 per second. So the answer here is 4.61 times 10 power of 9. So this is the number. So this answer for source of 1 second and 1 day. So you can try for 1 hour. Okay. So next question, you can see here, how many decays between t equal 0 and t equal 1 hour? So we try to find the how many decays for t equal 0 to t equal to 1 hour. 1 hour. So here just to recap, n is equal to n naught exponential minus lambda t. Lambda is similar, which is decay constant, okay? And n naught is the initial quantity of the radioactive nuclei, and n is the remaining quantity of the nuclei, okay, that we calculate. So here we try to find the decay between t equal 0 to t equal to 1 hour. So we need to use this equation, delta n, so which is equal to n naught exponential minus lambda t for t equal 0 here, minus n naught for exponential minus lambda for t plus delta t for another t. So we can rearrange here, n naught factorize n naught, right, exponential minus lambda t. This one, okay, just to recap here, is equal to minus exponential minus lambda t times exponential minus lambda delta t. So we can still factorize here. What we have here is exponential minus lambda t. So this one is equal to 1 minus the balance here is exponential minus lambda delta t. And to make it easier, because we are using here for t equal to 0, here exponential 0 is equal to 1. So automatically this one is equal to 1. So what we have here, and delta n is equal to n naught 1 minus exponential minus lambda delta t. So first calculation for delta n for 1 second. Alright, so we are using the same value of 1 second. So we have here n for 1 second. We can check the value here. N for 1 second is 5.34 times 10 power of 4. So we have here 5.34 times 10 power of 4. We have here 1 minus exponential. The lambda for 1 second source is 0.693 here. So minus lambda, okay, my 0.693. And for delta t, okay, delta t here, because the value here is 1 hour. So 1 hour equal to 1 hour is equal to 30 minutes, 60 minutes, sorry. 30 minutes, 60 minutes. Here is equal to 60 minutes. 1 minute is 60 seconds. Okay, 3,600. So here 3,600 for delta t. So the answer here is 5.34 times 10 power of 4. Another source, which is 1 day. Okay, change pen to purple here to make it easier. Okay, for 1 day, okay, maybe clean up here first. So we discuss this for 1 day half-life source. So we, for n, here this value 4.6 times 10 power of 9. So n will be 4.61 times 10 power of 9. Alright. Similar here, 1 minus exponential minus lambda delta t. So lambda here is 8.02 times 10 power of minus 6. And then the delta t is equal here 3,600, since that this is for 1 hour. So the value for a number of nuclear ready for the certain stage from 0 to 1 hour. So what we have here is 1.31 times 10 power of 8. Alright, so this is the calculation. So that's all for this question. We can see for the next question, inshallah. Assalamualaikum.